42. In this problem, you're told you pay $10 and roll a die. If you get a 6, you win $50. If not, you get to roll again. If you get a 6 the second time, you get your $10 back. So the first thing is create a probability model for this game. Well, this is what's called, we have this in the previous section, a discrete random variable. That is, there are separate, discontinuous outcomes, x's, if you will, okay? And namely, there's 3. You can win $40. That's if you roll a 6 on the first throw. Or you can win nothing if you don't roll a 6 on the first throw and you roll a 6 on the second throw. Then you get your $10 back, so you've won nothing. Or you cannot roll a 6 on the first throw and not roll a 6 on the second throw, and then you lose your original $10. So there's 3 discrete outcomes: $40, $0 in terms of winnings, and -10. So what's the probability you win $40? 1 out of 6 if you roll a 6 on the first throw. What's the probability you win 0? Well, that's 5 out of 6. That's the probability you don't roll a 6 on the first throw, times 1 out of 6, the probability you do roll a 6 on the second throw. And the probability of losing $10 is 5 out of 6 times 5 out of 6. That is no 6 on the first throw and no 6 on the second throw. Now, if you take these probabilities, 1/6 is 6 out of 36, plus 5 out of 36, that's 11, plus 25 out of 36, that makes 36 out of 36. So all the probabilities add up to 1. Now, if you take these events, you can take the specific x's, 40, and put them into L1, 0, and -10. Then go to L2 and put in the probabilities. 1 divided by 6, that's the probability that you win $40. Okay. 5 divided by 36, that's the probability that you win nothing. And then 25 out of 36, that's the probability that you lose $10. So then you're going to go to Stat and Calc, one variable stats, and you're going to run them on L1 and L2. Now notice that n equals 1. That's good. That means all the probabilities added up to 1. Now the average winnings is -28 cents. -0.27 repeating, so -0.28. We'll round it up to a penny. What's the standard deviation? Standard deviation is big, $18.33. Okay, and so that's the probability model. The mean is -28 cents. This is the answer for B. I already answered it. And the standard deviation is $18.33. Now, so that's A and B for 42. C, you play the game 5 times. Find the expected value and standard deviation of your average winnings. Okay, well, you play 5 times. You expect to lose 28 cents every time you play. So your expected winnings are -$1.40, or 5 times -28 cents. That's how much you expect to win. You expect to lose $1.40. Now, what's the standard deviation? It's going to be the variance times 5. Square root of the variance times 5. The variance is the standard deviation squared. And you got 5 variances for 5 times you play. So it's 18.33 squared plus 18.33 squared, etc. Or simply 5 times 18.33 squared for $40.99. So for 5 plays, you expect to lose $1.40 with a standard deviation of about $41. D. 100 people play this game. What's the probability the person running the game makes a profit? All right. Well, 100 people play the game. Now, let's talk about if we can use the normal model. Let's see. Well, it's random for one thing. Okay, we know that it's random because you're rolling a die. We know that each roll is independent, and each game is independent of each other. Again, because of the randomness of how the game is played. 100 is less than 10% of all possible games, which are, in fact, infinite, since you're playing a game in which there is no limit to how big the population of the number of these games can be. And finally, NP, and let's see, NP and NQ are both greater than, NP and NQ. NP and NQ don't enter into it, okay? But the first 3 rules do. So we have a mean and standard deviation, because this isn't a proportion, what I was thinking. It's not a proportion problem. Anyway, NP and NQ are not issues. But it's random and independent. Anyway, so what's the probability with 100 people playing that you make a profit? So the expected amount of money that those 100 people are going to lose is 100 times 28 cents, or negative $28. So people are going to lose $28. They're going to lose 28. So the profit is going to be $28. The standard deviation is going to be 100 times 18.33 squared, or $183.30. Now 0 is the point at which the people running the game make money. To the right of 0, over here, this is where they're losing money. This is where the players are winning money, over here. And over here is where the players are losing money. And this is where the owners are winning money, and over here is where the owners are losing money. That is, here's where to the right and to the left of 0 is the demarcation point. So we need to find the z-score of 0. So we're going to do y minus mu over sigma. So that's going to be $28 divided by 183.3. And so that z-score is 0.1527 right here. Okay, 0.1527 is the z-score of 0. Now we're going to shade to the right because we want to know the area to the right of the curve. I'm sorry, area to the left of 0. So we want to take the area from negative 99 to 0. So we'll do a normal CDF, negative 99, comma, 0.1527, which is approximately equal to 0.561. So the probability that the casino or whatever is going to make money on this game is 0.561. So that's 42. 51B. Okay, now I answered A, but I forgot to do B. Let's go to 51. Okay. So we use a sampling distribution. We want to know if the total can be greater than $500. And we figure out that not very likely that total tips exceed $500 for 60 customers. Now, the question is, how much does he earn on the best 10% of such weekends? Okay, so we're going to do the best 10%. I'm going to kind of work it in here. Best 10%. So we're going to do an inverse norm. Now what we can do is we can do an inverse norm for 3. Now remember, the best 10% is going to be 0.9. Inverse norm goes from left to right. So we want, let's draw a little curve here. So here's 9.6. So we want the best 10%. So we want to know what dollar amount, what average dollar amount of tips goes with the best 10%. So if we put in the mean and standard deviation along with the inverse norm, then it'll tell us what that number is. So the best 10% means that we're going to do inverse norm, starts from left and goes to right, so that's going to be 0.9. So 0.9 comma 9.6 comma, then the standard deviation is 0.8538. So on the best 10%, he's going to earn about $10.70 on average tip per meal. So he's going to make a little over $400. There's no, on the best 10%, not $500. Okay, finally 54D. Okay. Now 54D, here's the deal. A neighboring farmer has 10 Ayrshires. What's the probability that his herd averages at least 5 pounds higher than the average for Part C's Jersey herd? Okay, so the Jersey herd, we already figured out it's approximately normal, 43, 1.118, based on the size. We're doing a sampling distribution. The size with I think there's 10 altogether in that herd, or 20. Yeah, 20. Okay, so it's a standard deviation 5 over the square root of 20. Okay, now the Ayrshire herd is just 10, so it's 47, 6 divided by the square root of 10. Okay, so the mean is 47, and the standard deviation for the sampling distribution is 1.897. So the same preconditions hold. Now we want to know the expected amount of the difference. Now in D we want to know what's probably the average at least 5 pounds. Well, on average they should have a 4-pound difference. Okay? And the standard deviation of that difference is going to be the square root of the sum of the variances. 1.118 squared plus 1.897 squared. So the standard deviation of the difference is 2.2023. So here's 5 pounds. This is the area in which the Ayrshires average at least 5 pounds more. So the z-score is 5 minus 4 divided by 2.2023, which is approximately 0.454. So it's normal CDF, 0.454, 99, or approximately 0.329. The probability that Ayrshires average at least 5 pounds more than Jerseys is 0.329.